Thank you. So the aim today is then now to describe the ingredients involved in the proofs of this main theorem I stated yesterday. So remember that I had a Heath-Brown proved a result for hypersurfaces that all points in a certain congruence class satisfy a further equation if they are sufficiently close. And I then proposed the generalization to projective varieties of arbitrary codimension. But that was also more complicated to state. I used Chow weights and so on. So that theorem is proved using so-called determinant method. So I would now like to describe this method and discuss the proof. So as yesterday, I will always be embedded projective variety. So this is closed subvariety. Geometrical integral, I think integral was sufficing for almost all arguments, but let's say what variety means geometrical integral of dimension x, then is always equal to r, and degree of x is equal to d. And then I will need a model because I want to specialize modulo P, so then I take the scheme theoretical closure. And finally, then I would like now to count integral points which lie inside boxes and see, try to find upper estimates. So then I will use the same notation as yesterday, that this is then, if I have n plus 1 real numbers, this is then the set of all x belonging then to this closure such that this coordinate here, xi, is smaller than bi. So if, say, then b1, b0, b1, bn of at least 1. So these are then represented by integral primitive n plus 1 tuples up to sign. So I mean this has a meaning, I mean this condition here. So now then, let me then describe the determinant method. I should do it here. The determinant method. The first paper was a paper on affine plane curves by Bombieri-Pila, and then it was largely expanded by Heath-Brown, who looked at arbitrary hypersurfaces, but still there was only one equation. So what I would like to do now is to discuss it for arbitrary projective variety. And you can subsume into that case the case of affine varieties as well, because you just put one first coordinate to 1. So these results will also include, I mean, Bombieri-Pila's results. But I will use a P-Adic version here. So let us then fix a class here, y, on xp, on fp, and suppose that this is non-singular then. You can use this result as well for residue class of singular points, but the result you get is worse. So there is always an advantage, because in principle I would like to use the P-Adic implicit function theorem, and I can't really do that if it's not non-singular. And then I will then consider then this homogeneous coordinate ring here, S of k at least 0, and this is then the homogeneous coordinate ring, and let then this be the homogeneous coordinate ring. So this is then given by, you have these coordinates, and then you have some homogeneous ideal here, and I will then look at the Hilbert functions. H of k be the dimension of S of k. So what I will do now is that I will form a determinant with, I will take a monomial basis of this vector space, and then I will evaluate it at hk points inside this box, inside this set here. And then I will first prove that it's bounded from above, and then I will try to prove that it has a factor which is bigger than that bound. So then this determinant will vanish, and then we will get a new equation. So let then here So I take then here, maybe I continue here. So let then here x a of 1. So I need some notation here. I always run short of letters here, so maybe I already used this here, but a for some other purpose. So, but I think I will today. It will only have one meaning here. X a1 n, and then I will then have then here x of a of n. So this is kind of vector notation. So x so the last one is then hk. So I will take a monomial basis here. So this will then be the first coordinate, and the last one will then be a hk n 0 1 0 n n. So I hope this notation is clear. So this should be an index here. So let me write h of k here. This is the last one. So let this then be a monomial basis, of sk, and let then here. So I take the same number of points, p1, ph of k, then belongs to this set I want to study, x, z, b0 up to bn, and then I will also assume then that they are in the same congruence class modulo p. By the way, p could be replaced by any integer. I mean, you can consider modulo 6 or modulo 10 or modulo 12 if you just give this a meaning of non-singular. So it will work. So, but I mean, I want to explain it in the simplest case for pedagogical reasons here. And form then the following determinant. So I will call this m in the sequel here. So m will then be, I will take all these monomials, x a of 1, of p1, and then I will take then here x a of n, x a of n, let's see here so I get it right, a1 up to p h of k. So this is the first row, and the last one is then you take the last monomial and you evaluate it in all the points here. X a h of k, and you evaluate it in p h of k. Of course, these are well defined only up to sign, but you choose one representative and then you form this. And anyway, we'll just be interested in the size of this determinant, so the signs will not play any role. So we will. So now the method is then as follows. We make some easy easy observations here. So then this determinant of m is then bounded in terms in terms of this b0 bn. Since I'm in this box, so I don't use this y yet. So I only use that I'm inside this box. So and this is quite tricky to estimate the determinant. Maybe you might think that's very easy, but it will turn out I will need a geometric invariant theory to get the right bound. So, but if we have an hypercube, so if b0, then everything is trivial. Then a determinant of m is then smaller than b k times h of k. Well, you have this h factor as well. You just use the definition of determinant, and then you know, I mean, each product here you can estimate, and it's just bk, I mean, each term, each factor, and then you get, of course, this. So the complications you have if you're in lopsided boxes, then to deal with them, you need something more sophisticated, like the geometric invariant theory of Mumford. So this is something I will explain. And this problem to bound these determinants occur also in many other contexts, in Diophantine approximation, in this paper of Evertse-Ferretti, but also in papers on Keller-Einstein metrics, so which I'm inspired by. So I will come to that. But there is another thing you have to do. Then you also have to prove that this determinant of m is divisible by high p power. And you can get, because you have congruences between these points, I mean, if you just multiply them with some constant, you can find representatives with a congruent modulo P, and then you will have congruences for the modules, for the monomials as well. And by elementary transformations, you can easily prove, if you have the implicit function theorem, you can easily prove that this is divisible by a P factor. Maybe I will do that tomorrow rather. So today I will more concentrate on this. But let me just point out then that by the, say, the P-Adic implicit function theorem, P-Adic, I don't know how who used it systematically, but for instance in Weil's book on adels and algebraic groups, he used it systematically to look at measures, volume, P-Adic volumes, and so on. So it's probably much older. So that is one ingredient. So now we have a number which is bounded from above, but which is divisible by a high number. So if P is sufficiently large compared to this, if P is sufficiently large compared to B0, B1, and Bn, then this determinant will vanish. And this means that we will get a new equation for these points. And we get a new equation of degree k for P1 up to P of h of k. Because if this determinant is 0, it means that some linear combinations of these monomials will vanish at all those points. And since this is true for any set of hk points, I mean, I choose the same number, then this means that all points in this set will lie in this equation. So what we get is that this x, if you take all the points here, B0 up to Bn, and all those reduced to P then, so is then contained in Z, while X is not contained in Z, for some hypersurface of degree K. So, of course, you can formulate this if you want in oracle of theory, or it's a bit artificial because it's so easy. But the main idea is simply that if you have an integer with a bound which is smaller than the p power, then this will be 0, this integer. But I mean, you can formulate everything in terms of oracle of theory, this idea. And I myself, I do not really use oracle of theorem, but I'm inspired by comparison with function field case, and then often I can use geometric arguments. If I have fp, then you can look at rational curves and so on. So it's very useful to compare this with function field. So I got questions before, why are there no papers on functional case? It's simply that the people who are interested in these problems, for them Q has a much higher status than rational function field. But this doesn't mean that this method doesn't work in the function field case. It even works better. But here in my talk, I will only discuss a number field case, and I will concentrate on Q. So how can I erase this?
Top button, you press once.
What?
Press it once.
Once, just? No. Is it wrong? The middle button?
The top one.
Top one. Ah, okay. Yeah, thank you. Okay, so the idea is very simple, and you think, but it turns out that to really prove anything useful, you still requires quite a lot of machinery. So now then, I would like to study then the following problem, namely to bound the aspect 1 today. And already that will not, we need some time. So let me first then say that we have the trivial, we have the following trivial estimate. So if I have then this monomial basis, and for then the monomial basis, So I already gave you one estimate here in case we have a hypercube here, but I can push it a little bit further then. So for a monomial basis in xa1, and I just explain this notation then here, a h of k of sk, then you have, of course, that the determinant of this, this one I want to bound, this is smaller than, so I have then hk faculty, and then I have then here I go from 1 to k to h of k, and then since they lie in this box, so whenever I take any term here, I can just put these b coordinates instead of the coordinates for the point to give an upper bound for each term. So what I get here is the following bound. So I have then here b0, and then I have this exponent here, a I0, and then I have b1, a I1, and so on. And the last one is then bn, and then I have ai n. So this is an obvious bound. So the problem you're faced with is then to try to minimize this bound among all possible monomial bases. And then study the asymptotic behavior of that bound. So the problem is then the following: that how does this bound? So it's exactly the same expression then here. B0, it's the same expression then here, Bn, so I do not repeat it, it's the same. How does this grow when k goes to infinity and we choose the monomials, nomial bases x a0 up to x hk, such that this product is minimal, such that the product is minimal. I mean, there is a minimal choice because I only find many monomial bases for each k, so I want to study that, and I want to study what happens when k goes to infinity. And at the end, the solution of that problem will lead to this Chow form, this Chow coordinates I described yesterday. So there will be Hilbert weights and there will be Chow weights. And to solve this problem, the geometric invariance here of Mumford enters very naturally. So let me just stress that this has been studied independently, this problem, in other contexts, which I've already mentioned. So it's amazing, it pops up a bit everywhere. So this problem also occurs in papers of so I have already mentioned this Evert-Ferretti. This is then Diophantine inequalities on projective varieties. I think in the International Mathematical Research Notices, but there is only one paper with that name. And there they gave an alternative proof of the Faltings-Wistol's theorem, and they have a different approach. They use Veronese embeddings and various powers of these coordinates, and they were also faced with this problem. It's just that in that paper, when I take minimal, they always take maximal and vice versa. So everything is upside down. But if you just make this translation, you will see the similarities. And the paper which inspired me was rather a paper by Paul and Chan. I mean, there are many Chan. I suppose it's the most famous one. I mean, competing with Donaldson on Keller-Einstein metrics. Competed with other Chinese, many Chinese working on that. So that paper, I think, was never published. It's on archive. It's generalized Futaki invariants. Futaki invariants. It's on archive. So if you Google Futaki and Chan, I think, or Paul, I think that will work. But if you just take Paul and Chan, I mean, you will get many hits. So if you just do Google with Futaki, I think you will easily find it. Or you use, I should say that there is a, when you look at Keller-Einstein metrics, there's a geometric stability criteria called K-stability. So that you expect now it's solved that you should have a metric if and only if that occurs. And then there was an old invariant of Futaki, which then Donaldson reinterpreted. And to do that, he constructions which are very similar to here. So therefore, I will talk about Donaldson's test configurations and so on. So I was more inspired by that paper than I discovered that afterwards, in fact. So I didn't know about this. And also normalizations of the y's are the same as on the Keller-Einstein metric. So let me just say here then that the solution here, I mean, we all rely on Mumford's geometric solution uses and here Mumford's geometric invariant theory. So first is book, and then there is a well-quoted paper in L'enseignement mathématique, Stability on Projective Varieties. So that will contain very crucial ingredients to give a complete solution of this. So now then I would do some abstract nonsense here. What I will do is that I will deform this variety slightly. So I will have a family over A1 such that this deformed variety would have simpler equations. So let me explain this. Following notation then, so I will then take T will then be equal to the set of all T0 up to Tn of Gmn plus 1. So this will be a n-dimensional torus such that T0, T1, Tn is equal to 1. So I view this as an algebraic, commutative algebraic group. And then I will look at the Hilbert scheme. So it will not play an essential role. So if you don't want to know what a Hilbert scheme is, I think most of you do, I will explain this families of, I mean, I will deform this variety a bit. I will consider families of such varieties X. I will give them explicitly. But I mean, it's a more elegant, since I want to have group action, so it's more natural to still devise to introduce a Hilbert scheme here. Of course, if this group will act on this. A Hilbert scheme of then subschemes of P and K, P and Q. I only do it over Q. Of course, this works over many other fields, and even over Z over Q with the same Hilbert polynomial as X. So here is an important point, that because afterwards I want to have everything only to depend on D and N, and in general you can have infinitely many Hilbert polynomials if you take all schemes of degree D and dimension R. But if I assume that it's reduced, or that it's even if it's integral, then there are only finitely many Hilbert polynomials. So this I will use. So there will only be finitely many families for a given degree and dimension. So because I want to have uniform estimates. So that is something I will use. And then I will now have then here the, let's see here. So, and then with an F will then be the universal family. So I have a universal family. So for each point there it parameterizes some variety of dimension R and degree D. So this will then be the universal family. And then I need a name for the projection also. So I let P will then be the projections from F to this Hilbert scheme. So then the fibers of this are then varieties of dimension R degree. This is then the projection onto H. And now the point is now the following, that the T action on Pn, it will then induce an action on F. It will then induce an action on the Hilbert scheme. So the T action on Pn here, it will now induce it's an obvious action here. You just multiply each coordinate by those, each coordinate by coordinate. You use this torus, induces then T actions on. So I have T actions then on all those schemes, on H and F, such that this P is T equivariant. So this means that if I act here and then it commutes with the image, so this means in particular that I can now, let's say then I start with my one point here parameterizes x. So what I will do is that I will look at the orbit given by that point. So I think I can remove all this. So let's continue here. So I will now first give a family parameterized by T, and then I will look at one parameter subgroup, so then I will get families over GM. And then you can extend them to families over A1. And this is what Donaldson did, so I will call those test configurations. And it will turn out that these test configurations are very useful when you try to analyze these, estimate these determinants here. So this is a method, for instance, used by Paul and Chan and many other people. Sorry? Yes? Yeah, but usually in geometric invariant theory, you so to say you lift, so to say, this PGL action to an SL action on a reductive group. So I'm maybe I can do it otherwise, but I'm so used to this Mumford's book. I mean, strangely enough, I was rather old when I really read this book, and then I discovered that a lot in that book. I mean, I've had it in my bookshelves, but I should have read it earlier. So, yeah. So okay. So now what I do the following. So now I fix. So if then H now in HQ represents then here X of H, X in Pn. Then we get a family. Then we get T equivariant family then. So I pull back this F, so I have then F over T. So did I give this a name here, PT? By in over then T times H for all T belonging to T, so to say. So I let this act T, and then so one will corresponding to X. So the fiber over then 1 will corresponds then to should I say T over Q? It will correspond to X. So this is then the first step. Now it's convenient now to, instead of to simplify it a bit to look at one parameter subgroups then here. But let me just give you the equations here so you should not be frightened for this abstract nonsense here. So we have then here equations for this family f of t, and this will then lie in Pn cross t for those who are not used to these abstract notions. So say in Sweden, I mean, it's possible to give definitions like that. So if x on Pn is then defined by f1 equal to fs equal to 0, then this f of t contained in Pn cross t is then defined by, so you just introduce more coordinates, I mean corresponding to this. So you have then here f1 of t0, x0, etc., tn. So you have the same equations, just you perturb, I mean, these coordinates by these actions here, but you have in principle the same equations. And here tn, let's see here, t, did I write it correctly here? T0 here, sorry. One moment here. If tn, yes, fs here, sorry. It's just x0, tn, xn equal to 0. So it's a very simple construction. I mean, you can phrase it without this abstract nonsense. I mean, if you write, it's a bit ugly to write, choose equations, and I want you to, I will strongly use the fact that everything is equivariant, and so to some extent I prefer this more abstract definitions. So, but this is not the main point, these are just definitions. So let me now tell you how you use this, and this is, I will then use this name here. I will call it Donaldson's. I mean, he used it for completely different purpose. I mean, he used it to generalize his Futaki invariants, and to some extent that is more sophisticated. You look at second coefficients of these Hilbert polynomials as well. So I would not, it's a good name to call it test configurations. So this is a test for, his is a test for K stability, but here it will rather be a test for Chow stability or Hilbert stability, so, or Hilbert semi-stability rather. So let me then explain that. So if now lambda gm of t, so I will then look at one parameter subgroup. So I will then have here t goes to lambda 0 up to t lambda n is a one parameter subgroup, one parameter subgroup. So just like a Mumford, I will just write one PS. I mean, it will work also if you have the trivial embedding, if you send everything to one, but it's totally meaningless. So I will still call it one parameter subgroup. I mean, it will include that case as well. I mean, there is no reason to even discuss that. So with then here, so this means for this to work then, to satisfy this condition, then you need then here that this n plus 1 tuple, the sum will be 0. So I will put a 0 here when I take this n plus 1 tuple. So this is just the kernel from set n plus 1 to z, where I take the sum of all the coordinates here. So I think it's clear what I mean. The sum should be 0 here. So then, if then we have this, then we get the family. Then we get an even smaller family, which I will denote by p lambda from, and then I will have some scheme here over then gm by pulling back this family I had over the torus along this lambda from jm to t. So this means then that this action then, I will then multiply the coordinates by these powers of t. So now maybe you will already see the similarity between the statement when I discussed the formulate the main theorem with Chauvites yesterday. So, but this will then be an intermediate steps to consider such families. And now I will then use a evaluative criterion for properness. So I have now a morphism from GM to the Hilbert scheme, and since the Hilbert scheme is proper, I can extend it to a family. I can even extend it to P1, but I will only need to extend it to A1. And then I will be interested in the degeneration. I mean the fiber at 0. So this is then what I will call the test configuration. And once you have such this morphism, you can start to discuss weights and so on. So I have such a family. So this family has a unique extension, has a unique extension to a family. So I will now call it X script or to A1, and I will call this here P lambda bar, and this is to see this use then evaluative criterion for properness of H. So, so this is a kind of families you see many papers on, recent papers on Keller-Einstein metrics. So now you have that this is J invariant, so this is JM equivariant. So then I have then here a notation then that x lambda is then the fiber of this P lambda bar at 0 belonging to A1. So once you have that, since this you have this map is a JM equivariant, there is a JM action on this fiber. Now there is now a natural GM action on X lambda as this P lambda bar is a JM equivariant. So now the next step is now that I will look now at the homogeneous coordinate ring of that, and I will study weights of these JM actions of various vector spaces. And these weights will then correspond to exponents for various bounds for the minimal determinants here. So it boils down to such problems on these weights on actions on this homogeneous coordinate ring on this deformation of X. Maybe it looked artificial the first time, but second time it's extremely natural. Look at it. So I will try to explain everything involved here. 20 minutes. So unfortunately, this lecture would rather be 90 minutes. So I probably need to interrupt 60 minutes. I will maybe not reach a fantastic conclusion today, but maybe tomorrow. So let me just make a remark that this, I've already said that this JM acts on this, and in principle then that this X lambda in Pn should view it as a degeneration of X, and the defining equations, have often then fewer monomials. I mean, you have different T actions on, you have different sort of weights on the various monomials, and when you let T goes to 0 here, you so to say kill some of the terms in the defining forms here. So you simplify, so you get some variety which is simpler than the original one. And if you look at the other papers, So when we first formulate this determinant method, student and I, then we use so-called Gröbner basis techniques. We use graded monomial orderings. And the idea there is that you replace an ideal by leading terms with respect to a Gröbner basis. And this is something similar, that you, so to say, replace equations by similar equations. And if this BI, if the log of these BIs are Q-linear independent, then the leading terms there will just be one leading term, and then this will simplify a lot. I mean, it will be a monomial ideal. So this is a link between what we did before and what we do now. But it's a more elegant formulation, I mean, of what we did in, and this also corresponds to the stuff in this paper by Evertse Ferretti. They also have similar constructions. So now then I would like to discuss then Hilbert weights, which I will then relate to this, finally will relate to the Chow weights I used in the formulation of the theorem, but that maybe I will only have time to do tomorrow. But in Hilbert's texts, then in Mumford's text, they are clearly explain their link between Hilbert weights and Chow weights. So finally everything will depend on the results of Mumford. So let me then just discuss now Hilbert K weights, or maybe K Hilbert weights. I don't know exactly how you say K Hilbert weights. So I think these notions occur already in this famous paper by Giesecker, where he solved the conjecture for Mumford for surfaces of general type. So it's not new, these notions. Maybe of X with respect then to. So now I will then have such a one parameter subgroup, but any one parameter subgroup of this torus is generated by, can be explained by these exponents here. So all this is still, my goal is still to bound this determinant. So if you wonder what is going on here. So, okay. So let then here Q x0. So now I will look at the homogeneous coordinate ring, not of the original variety, but of this deformed, this degenerated variety, x lambda. I lambda, so this will, I will now denote it by S of lambda. So this will now be here the sum of sk of lambda, where k is at least 0 here, be the homogeneous coordinate ring then, coordinate ring of x lambda. Did I put it lambda? I think I put it above Pn. And then now I have a JM action then here. So then I have the following definition then here. So first then the weight lambda x of I. So I will write the exponent in this form now, of a monomial x I equal then to x0, I0, xn, in. So this is a weight then, the weight of this monomial with respect to this one parameter subgroup is simply then lambda 0, I0 plus lambda 1. So it's a kind of scalar product between these two n plus 1 tuples. So this is a notion of white. Maybe I should add here with respect to lambda. So now I have defined then the weight of a monomial, but now I want to define the weight of these vector spaces, and then I look at all monomial bases here. So maybe then I can remove everything here. So I have a GM action on this graded algebra S lambda, and I look at each graded object, I mean each vector space, and then I have an action of GM, and then I can define weights on each such vector space in each degree. And it would be some kind of Hilbert function. They behave a bit like Hilbert polynomials and so on. And this is what we will analyze. So 2, I defined then here the following here, that the vk of lambda of x is then, sorry, let me just write some text there. So the weight here of sk lambda, or if you want, of or the k Hilbert weight, of x with respect to lambda is given. So this is then, I will denote it by wk lambda of x is then equal to the minimum. So here I look at all monomial bases, a1 up to a of h of k. And then I take the sum of all those weights I just defined for each monomial. I have already defined the base, so I have then here the weights with respect to lambda of this x of a of I. So I have that many monomials of degree k. So now I look at this sum among all monomial bases here, where then here a1, so to say, up to a hk run over all monomial bases of sk lambda. So these are now my definitions of these weights. So why do I introduce them? This is because I want to now to bound these determinants, and I will do that in a moment. So let me just, before I continue, explain that there is a link here between the these. So these weights are defined for x lambda, but they will, so to say, converge to the converge in a certain sense to the Chow weight, which is defined in both cases. And the Chow weights of this deformed variety is the same as the Chow weight of the original variety. And also the Hilbert functions. And you can also relate bases of monomial bases of x, which are minimal, to monomial bases of this deformed variety. So this is an important technique, I mean, to do this transition. So in our previous paper, we just directly started with Gröbner basis, and we defined then this exponent in terms of you can say in terms of x lambda. But now here we want to have a more elegant formulation, and then we need to do a transition between x and the generated variety. So let me just make some remark before I continue with Mumford's function, because these functions occur in Mumford's book, I mean, chapter 2 already. So I will just give a lemma here, which I will need later, because it's very hard to prove uniformity if you work directly with these ideals. But if you work with the simpler varieties, x lambda, then they are basically, in many cases, given by monomial ideals. And monomial ideals are it's much simpler to obtain uniformity. So you need to do this deformation, the generation, to get uniformity in this asymptotic estimates. So this is a reason. So let me just write then that this, I have then here that the Hilbert polynomials, first that the Hilbert polynomials of x of k is equal to x of lambda, the Hilbert function. And you also have that these Chow weights I discussed yesterday, ax of ax, I call it then ax of lambda. I defined it even for reals, but we will study reals by approximating them by n tuples of rational numbers. And these n tuples of rational numbers will be given by defined by starting with integral n plus 1 tuple. So in a moment I will extend this to reals here. So I will have, you can extend this to real, lambda could be a real n plus 1 tuple with some 0. And then we are back to what we did yesterday. So yesterday I defined then these Chow weights, and this is now the same as AX. I can define the Chow weight here of lambda here. So let me just tell you a little bit about the proof, because this also gives you information of this new variety X lambda and how we obtain it. So one uses that if X is defined by F1, so if you have then explicit homogeneous polynomials defining then X, so these are then homogeneous polynomials in n+1 coordinates here. Then this X lambda, this deformed variety, is defined by same number of polynomials then here, J1, where this is then so-called what I will call the leading term of Fi. And then I will do this here. One will run through, one will run, I will run between 1 and q then here. So I have the same number of homogeneous polynomials, but these are simpler, where then this Ji is defined by. So what I do is now that I let this torus then here, this one parameter subgroup then here act. So I let it act on each such defining equation, x0 up to t lambda n xn. And then I expand, and then I will get, just like for Chow forms, I will then get here t d0, I is then the first, and then I will get some lower terms, t d1, ji1, etc., plus t dv times ji of v. So I just plug in this and I expand, where then this t I have then here that this is d0 is smaller than d, is bigger than d1, etc. So this is the smallest term here, dv. And then I have that all those gi plus 1, they are then homogeneous polynomials in these variables. So this is very similar to the way I defined Chow weight. So when I study these functions here, then it's very important to understand, I mean, the relation between x and the relation between x lambda. And in the case where this log of these bi's are Q-linearly independent, then these leading terms will just be monomials, and we can actually reduce to that case. And then everything is very simple because we have monomial ideals. So this is one very important ingredient. So now then I like to say something then about Mumford's result and how it's used. So this was this, yes, here. So you have seen these functions, these weights I have defined. So this was just an intermezzo. I will only use it later, but it helps to understand what's going on. It will be needed in the proof of just of bounding these determinants, this lemma there. So we have now that these functions, the weights then here, vk of lambda of x, they define a function which is a function, it depends on k and it depends on the variety. So from all the set of all one parameter subgroups of this torus, which is in fact then equal, if you want, to set 0 n plus 1. So if we have such a one parameter subgroup, we send it then to these exponents here. And that we have then a map here. We have just defined the weights here. And this which is studied then in Mumford's book. Geometric invariant theory. So and he writes then here of course, he does everything in the opposite way here. So mu k is equal to minus wk and so on. So he introduces something called the flag complex, which is kind of, I think people call it sphere, Tits call it buildings or something, and then he can parameterize all those test functions if you want. So if you want to have a very good background to what I'm doing here, you could just open this this book, and even more, maybe his paper Stability on Projective Varieties. So let me just extract then here one result from that book, which is very useful here in this context, and we'll look at these weights. So still you should not forget that the goal is to estimate the number of rational points. So it's a rather big tour we will make here, but I hope I will be able to give you applications here. So we have the following proposition. Mumford chapter 2 in this GIT. So he proved the following, that this function here, v lambda x, is piecewise linear. And you have, of course, also here that the weight of lambda, if you multiply with a positive number, then it's linear in this sense. So you have that for all n and all such weights. Or lambda in this n plus 1. So now what you would like to do is, since you have this homogeneity, you can extend this to rational n plus 1 tuples with some 0, because you can just multiply it by some integer, common integer, then you get an integer multiple, so you can just extend it to q. But then it turns out that this is continuous, so you can extend it to a continuous function. And this corresponds a bit just to that you take here, put real exponents here instead of just integer exponents, like we did yesterday. So let me just write that down. I think it's explicitly in Mumford's book, or I don't have it here. There exists a unique extension of this vk of x to piecewise linear continuous function wk of x. So then I so to say tensorize this hom over z of all these one parameter subgroups, j to m to t. It maybe looks a bit artificial, but it corresponds just so that you send t to real exponent instead of just, so it's something non-algebraical in a certain sense, but you can identify this then with r0 n plus 1. I mean n plus 1 tuples with some r, and this is now sent to r. And where then these weights will have then the same property if you multiply with a positive. So you will have that the weight of u of lambda will be equal to u weight of lambda for all u in R positive reals, and you have for all lambda belonging to R 0 n plus 1. So you can say that this extended function is uniquely determined by the weights I have just defined. So now we have a notion of Hilbert weights. So as I say, I just have to find a solution here. What I plan to say rather would have taken 70, 80 minutes. So what I will do now is that I will just formulate a proposition, and then I will now prove it some other time. So this is now, will give you some hint still, the relation of this definitions to the problem I posed in the beginning of bounding the size of this determinant. So I think I have time to formulate it, but then maybe I will postpone the proof to tomorrow, because I want to have lunch just like everyone else. So we have then here a proposition then here. I think I will formulate it carefully since there's been so much stuff here now. So let then here h of k be equal now to the dimension s of k for the homogeneous coordinate rings. For the homogeneous coordinate ring, S equal to the sum of all sk, k at least 0, of x in Pn. So this is the first thing. So then there exists a monomial basis which I then called xa1 up to x h of k. No, this is an n-tuple here of integers. So the last one is I denote it like that. I have such a monomial basis with. So now I wanted to bound this determinant here. So then I want to evaluate then this xa1 in the first point I'm interested in, and I want to evaluate it until the last point. So I have the same number of integral points in this set, and then I form this determinant here, and then I have then here x a of h of k. So this is the last. So I have this I have this a of k functions which I evaluate then in these integral points, and then I have then here x h a of k of p a of k. Then this is then bounded by hk factor times n. So if it were just b everywhere, then I would have been done with this k h of k. B is a mean value here of all the bi's. So b here is then here equal to b0 bn 1 n plus 1. But now I have this extra factor, which explains why it's so much more complicated when you have a lopsided box. So you will then have now exp. And now you will have this weight here. And then what you insert here is you need then an n plus 1 tuple with sum 0. But this will now be log of b0 divided by b until then log of bn divided by b. So the sum here is 0, since b is a mean value here. So this is the bound you have. And this is then I will prove this tomorrow then, this is then a very important ingredient in the proof of this construction of these auxiliary polynomials. And the advantage with this bound is that this function is well understood. I mean, it has already been studied by in Mumford's texts. And what you do is that this will be some kind of polynomial, this function. And when you let k go to infinity, the leading term will be the Chow form, which I had yesterday. But I will explain all that tomorrow then. So I will connect everything tomorrow then. So, okay, thank you for your interest.